Welcome to today's explainer, everyone. Today we're diving headfirst into the high-stakes, absolutely fascinating world of embedded systems debugging. If you've ever found yourself wondering exactly how engineers track down the root cause when a complex piece of electronics just inexplicably gives up the ghost, well, you're in exactly the right place. We're going to treat this process like what it truly is, a high-tech detective story, where the clues are scattered across both the physical world and the digital realm. So, picture this. You're working on a product, testing it out, and suddenly the main motor just stops, completely dead. Now, if you were building a traditional web or desktop app, you just pull up a stack trace, right? But here in the embedded world, the suspect could literally be anywhere. Is there a logical bug in your firmware? Is it a slight voltage droop coming from the power supply? Or maybe it's a microscopic, microsecond timing glitch between two chips trying to talk to each other. When an embedded system fails, it's a total mystery. And the culprit could be the digital code just as easily as the physical hardware. All right, let's jump right into our game plan for today's explainer. We'll kick things off with the embedded system mystery, move into the battle of hardware versus software, then we'll spend some time profiling the suspects. After that, we'll crack open the ultimate toolkit, and finally, we'll talk about solving the case. So, kicking off section 1, the embedded system mystery. Let's talk about what makes these environments so unique. The stakes we are dealing with here are incredibly high. We aren't just talking about a web browser freezing up and annoying someone. Embedded systems are the brains inside automotive engine control units, critical life-saving medical devices, aerospace flight systems, and massive industrial robots. In these environments, an undetected defect doesn't just throw an error code on a monitor. It has serious, tangible, and potentially dangerous physical consequences. If a desktop app crashes, you're rebooted. If a medical device or a car's braking ECU crashes, the results can be catastrophic. That's exactly why debugging in this space isn't just basic troubleshooting. It's an absolutely vital life-or-death engineering skill. That brings us right into section 2, hardware versus software, which is basically a constant tug of war. You really have to appreciate the contrast here. In traditional software development, memory is practically infinite and timing is usually pretty flexible. But in the embedded world, you are severely constrained. You've got limited memory, tight power budgets, and critical real-time constraints. Plus, you have to debug the hardware and the software at the exact same time. Think about it. You can't just pause an embedded motor controller with a software breakpoint to look at your code. If you do, the software stops, but the physical momentum of that motor and the raw power running through the circuits, those definitely don't pause. Do that, and you might cause some real-world chaos. Moving on to section 3, let's start profiling the suspects and look at the really tricky bugs that keep engineers awake at night. Our first prime suspect is the infamous watchdog reset. You probably know the drill. If your firmware gets trapped in a loop or deadlocks, it fails to pet the hardware watchdog timer, and boom, you get a hard system reset. It's a vital safety net, sure, but figuring out exactly why the code hung in the milliseconds right before the hammer dropped, that is a massive headache to untangle. Then we have race conditions. These are incredibly common, especially if you're running a real-time operating system or RTOS. This happens when multiple tasks, or maybe an interrupt and a background loop, compete to access the same shared data or hardware resource at the exact same time. The truly infuriating thing about race conditions is that they usually only make the system fail under very specific, nearly impossible to replicate timing scenarios. Your system might run perfectly 99% of the time and then just inexplicably crash on a Tuesday afternoon. And finally, our third suspect, memory bugs. These might just be the stealthiest suspects of the entire bunch. We're talking about buffer overflows, invalid pointer accesses, stack overflows, the works. Why are they so sneaky? Because a memory bug can overwrite and corrupt a piece of data right now, but the system might happily keep running. It won't actually crash until much, much later in the execution when it finally tries to read that corrupted data. They are absolute experts at hiding their tracks. To catch these kinds of elusive suspects, we need to open up section 4, the ultimate toolkit. We need specialized gear. The key to embedded debugging is matching the specific problem to the precise tool required. Got a firmware crash? You're going to want to reach for a JTAG or SWD debugger so you can peer directly inside the processor's registers. Experiencing a communication failure on an SPI bus? Time to hook up the logic analyzer. But if you suspect a voltage brownout or a super noisy power supply, you bring in the oscilloscope. And for tracing those stealthy memory bugs we just talked about, you fire up a software debugger like GDB. Honestly, using the wrong tool in embedded systems is like trying to use a magnifying glass to listen to someone's heartbeat. It just doesn't work. Now, distinguishing between your hardware tools is crucial. An oscilloscope shows you the raw, unfiltered analog physics of the board. You see the electrical noise, the exact voltage levels, the messy rise and fall times of a signal over time. A logic analyzer, on the other hand, couldn't care less about the analog noise. It only cares about ones and zeros. It decodes the digital language and state changes, translating the high-speed conversation happening over protocols like UART, SPI, or I2C. Simply put, the oscilloscope shows you the physics, while the logic analyzer reads you the language. Aside from the physical hardware probes, we also lean heavily on software tools, with UART logging being a classic. It's basically blasting print statements out of a serial port. Now, UART logging is super easy to set up, but it is a massive double-edged sword. If you push too much text out of that serial port, you can actually choke the CPU and alter the system's real-time timing. It's the classic observer effect. You might end up fixing or hiding a timing bug simply by slowing the system down to observe it. All right, let's enter the final phase of our investigation in Section 5, Solving the Case. It's time to put it all together and follow the evidence. Let's look at how a structured methodology works in the real world. Say you have an STM32 microcontroller and its temperature sensor just stops sending data. You don't just start blindly guessing and changing code, you follow the evidence. Step 1, check the power supply. Is the sensor even getting juice? Step 2, verify the physical I2C wiring. Did a pin come loose? Step 3, hook up that logic analyzer to the data and clock lines to see if any digital communication is actually attempting to happen. Only after you have completely ruled out the physical world do you move to step 4, where you set breakpoints in the firmware and inspect the software data. Good debugging is always evidence-driven, never guess-driven. Now, to prevent these crazy mysteries from ever making it into the hands of a customer, engineers rely on something called hardware in the loop, or HIL testing. You can think of HIL as the ultimate interrogation room. It involves hooking up the actual physical embedded hardware to a heavily controlled, simulated computer environment. This lets engineers safely trick the hardware into thinking it's flying through extreme aerospace turbulence or driving down a snowy highway, reproducing incredibly complex real-world vaults on demand in a lab instead of waiting for a dangerous failure out in the real world. Of course, the landscape of our detective work is always evolving, and AI-assisted debugging is the newest rookie on the force. AI tools are getting great at chewing through massive gigabyte-sized system logs, explaining arcane compiler errors in plain English, and spotting suspicious code patterns. But there's a massive caveat we have to keep in mind. While AI is great at theorizing about the code, its theories still require strict validation against the physical hardware. An AI can theorize all day long, but at the end of the day, it can't reach over and plug an oscilloscope probe into a test point for you. Ultimately, the core philosophy from our source material boils down to this one perfectly stated quote: learn the code, understand the hardware, master the debugging process. True expertise in this field doesn't mean just being an amazing software developer, and it doesn't mean just being a great electrical engineer. It means standing right in the middle and successfully bridging the gap between digital logic and physical reality. Which leaves us with a pretty fascinating question to ponder. As embedded systems grow exponentially more complex, with IoT and smart devices literally everywhere, will AI eventually become smart enough to replace the need for hands-on physical hardware debugging? Or, by generating vastly more complex code at lightning speeds, is AI just going to make the mysteries we have to solve that much deeper? Thank you so much for joining me for today's Explainer. I really hope you found this investigation as captivating as I did, and that it leaves you eager to dig even deeper into the incredible, challenging world of embedded systems. Catch you next time.